Dear students, welcome again. We are on the chapter on semiconductors. Why semiconductors are being discussed specially? Now there are several reasons. One main reason is that the semiconductors are solids in which the conductivity is contributed twice. One by the motion of free electrons in the conduction band, and the other is the motion of holes in the valence band. They are equally important, as you must have noticed earlier this chapter when we were talking about the concept of holes in various boxes. Okay. Now today's topic is the intrinsic carrier concentration, and then we will discuss the extrinsic carrier concentration. Now what is intrinsic carrier concentration? It is the concentration in the pure semiconductors, that is no impurities added to the semiconductor. So the conductivity being contributed by the electrons and the holes in such solids, in pure solids, is known as the intrinsic carrier conductivity. Okay, we want the concentration of intrinsic carriers as a function of temperature in terms of the band gap. We do the calculation for simple parabolic band edges. We first calculate in terms of the chemical potential mu, the number of electrons excited to the conduction band at temperature T. In semiconductors physics, mu is called the Fermi level. At the temperature of interest, we may suppose for the conduction band of a semiconductor that epsilon minus mu is greater than the Boltzmann constant into T, so that the Fermi-Dirac distribution function reduces under this assumption. It reduces to this. You have read the Fermi-Dirac distribution function, but that function reduces to this form when epsilon minus mu is much larger than kpt. Let me show you the band diagram of a semiconductor. Now this is the band diagram of a semiconductor. We have the conduction band edge, we have the this is the valence band edge, and we have the conduction band edge, and right in the middle is the Fermi level. Now this is the energy versus the function of energy versus energy curve, energy scale. For statistical calculations, the Fermi distribution function is shown on the same scale. For a temperature Kb much less than Eg, the Fermi level mu is taken to lie well within the band gap as for intrinsic semiconductor. If epsilon is equal to mu, then F is equal to 1 over T. Okay. Now this is the Fermi-Dirac distribution function for this case for the electrons. Okay, this is the probability that a conduction band electron orbital is occupied in an approximation valid for the Fermi-Dirac distribution much less than 1. The energy of an electron in the conduction band is given by this. So you see, when the electron is excited from the valence band into the conduction band, it overcomes the band gap, which is equal to Eg, and then whichever level it occupies in the conduction band, that energy is also to be counted. So the total energy of the electron is then given by this expression, the energy of the electron in the energy level with wave vector k is equal to Eg that is the band gap energy plus h cut square k square over 2 me. This is the kinetic energy, because the electron in the conduction band is moving with a kinetic energy, and here the mass we are using of the electron is the effective mass, and k is the wave vector, h is the Planck's constant. So equation number 36 must be clearly understood. Okay, then we move on to the where EC is the energy at the conduction band edge, as in figure 18, which I have already shown you. Here me is the effective mass of an electron. Thus from equation 6.20, the density of states at epsilon is equal to this expression. So again we are using a density of states expression from chapter number 6, equation number 20. So you can see this equation at 6.20, and then you can understand that this equation becomes the density of states for the electrons becomes 1 over 2 pi square 2 me over h cut square power 3 over 2 epsilon minus EC. Now why we have taken, instead of epsilon we have taken epsilon minus EC, because we are measuring the energy of the electron right from the bottom of the conduction band. So we have to exclude this energy. Okay, so this is equation number 37, and now what we are interested in, we want to find that how many electrons have been excited to the conduction band at a given temperature T. You know that the semiconductor is insulator at the temperature T is equal to 0, which means that all the states in the valence band are completely full and all the states in the conduction band are completely empty. So when you raise the temperature from T above 0 degrees Kelvin, then the excitation of electrons happens, and the function which controls this excitation, which gives us the probability that the state in the conduction band, energy state epsilon, is filled. That's why we are using the Fermi-Dirac distribution function as given in equation 35. So now we are interested to find the number of electrons in the conduction band. Okay, now obviously this will be equal to the density of states of the electrons multiplied by the Fermi-Dirac distribution function for the electrons and the energy. So we have to integrate, because the electrons are scattered from the energy level EC to infinity. The energy band states, the conduction band states are between the energy EC, and it can go up to infinity. So this factor gives us the, along with integration, gives us the number of electrons. And when we substitute the values of density of states by equation 37, we substitute the value of F for the Fermi-Dirac distribution for the electrons as given by equation 35, and if we substitute these values here and integrate, we get this equation. Sorry, we have not yet integrated, but we have substituted the values. So equation number 38 is the result of the substitution of the values of the density of states and the Fermi-Dirac distribution function, and the integrand is epsilon minus EC exponential minus E over kBT into energy interval. So if we integrate this equation, the result is given by equation 39. So the number of conduction electrons or the number of electrons in the conduction band are then given by this expression: 2 effective mass, Boltzmann constant, temperature 2 pi h cut square power 3 by 2 exponential mu minus EC over kBT. Okay, so this is the number of electrons. Now as the electrons in the conduction band and the holes in the valence band are equally important, so we have to find the number of holes in the valence band at temperature T. So for that purpose we will require the Fermi-Dirac distribution function for holes, and this is obviously equal to 1 minus Fe, because Fe plus Fh will be equal to 1, so Fh will be equal to 1 minus Fe, and this is the value of Fe. And when we simplify this expression and approximate, equation number 40 is obtained. You can do this very easily, provided mu minus epsilon is much larger than kBT. Okay, then if the holes near the top of the valence band behave as particles with effective mass mh, the density of hole states is given by this equation 41, where EV is the energy at the valence band edge. Proceeding as in equation 38, we obtain the number of holes in the valence band again by a similar expression, that is the integration of the density of holes, the probability function of holes, but this time the limits are minus infinity to EC, because the holes are in the valence band, so we can have the limits from minus infinity up to the conduction band edge. So substituting again the values of the density of states and the Fermi-Dirac distribution function for holes and going through the integration, we get the value of P equal to this, the right hand side of equation 42. So here we have the effective mass of hole, Boltzmann constant, temperature, and the chemical potential, or we can say this is the Fermi level. Mu is equal to Fermi level epsilon F for as long as the semiconductors are concerned. Okay, so we have calculated the number of electrons in the conduction band and the number of holes in the valence band, and as I told you several times before, they are equally important. So for the concentration, equation 42 for the concentration P of the holes in the valence band. Okay, now let us multiply these together, N and P, to get the product NP, and we get this equal to given by the right hand side of equation 43. This useful result does not involve the Fermi level mu. So that is very interesting. When we multiply NP, we see that the Fermi level mu is no more there. So at approximately 300 degrees Kelvin, the value of NP is 2.10 into 10 to the power 19 per centimeter to the power 6, and equal to this. So this is the value of a typical value of the product NP, just to give you an idea of the magnitude of NP for actual band structures of silicon, germanium and gallium arsenide. So these three figures are for semiconductors: silicon, germanium and gallium arsenide. We have nowhere assumed in the derivation that the material is intrinsic. Okay, this means we have not indicated as yet what type of material is this. Is it a pure material or is it an impure material? So it means this equation is valid for both pure and impure materials, that is for intrinsic and extrinsic semiconductors. So this result holds for impurity ionization as well. The only assumption made is that the distance of the Fermi level from the edge of both bands is large in comparison with kBt. So a simple kinetic argument shows why the product Np is constant at a given temperature. Suppose that the equilibrium population of electrons and holes is maintained by the black body photon radiation. At temperature T, the photon generate electron hole pairs at a rate given by A function of T, while Bt and P is the rate of the combination of reaction this. Okay, so you go through these few pages over here, this paragraph over here, and let me discuss equation number 45. So we have shown that we know that the number of electrons in the conduction band must be equal to the number of holes in the valence band, because the holes are produced only when the electron jump from the valence band into the conduction band. So how many electron jumps to the conduction band, they leave an equal number of holes. So here is the stage where we are assuming that our material is intrinsic. So as long as the material is intrinsic, then number of electrons in the conduction band Ni must be equal to the number of holes in the valence band. So Ni must be equal to Pi, and from that previous product, if we calculate by taking the under root, we get Ni equal to Pi is equal to this right hand side of equation 45. Okay, now the intrinsic carrier concentration depends exponentially, as we see here, Eg over 2 kBt, where Eg is the energy gap. We set 39 equal to 42. So if we put these two equations equal, because this equation also gives us the number of electrons in the conduction band, and this equation also gives us the number of electrons in the conduction band, so we can equate them. So as soon as we equate these two equations and do a little bit of algebra, we get equations 47 and 46 and 47. Equation 47 is useful because it gives us the value of the Fermi level, and this is equal to half Eg plus 3 over 4 kBt natural log mH over me. So this equation is useful because it gives us the position of the Fermi level, which we are indicating by the chemical potential. Okay, now if the effective mass of the hole is taken equal to the effective mass of the electron, then this ratio will be 1, and you know that log 1 is 0. So in that case, mu will be exactly at equal to half Eg. What does this mean? This means that the Fermi level is exactly in the mid of the gap. Okay, so that's why we have shown the Fermi level in the mid of the band gap, because Fermi level is equal to half Eg. Okay, now we have been talking about the number of electrons and number of holes. Let's now talk about the intrinsic mobility. The mobility is the magnitude of the drift velocity of a charge carrier per unit electric field. So when we apply an electric field, this electric field accelerate the charge carriers, whether they are electrons or holes, and we have a term mu, which is the mobility. Now this mu must not be confused with the earlier mu, so we will write the earlier mu, which was the chemical potential, as epsilon f from now on, and we will write mu to represent the mobility. Mobility is defined by this equation, equation 42. This is the magnitude of the velocity of the charge carrier divided by the electric field. The mobility is defined to be positive for both electrons and holes, although their drift velocities are opposite in a given field. So mobility is always positive, whether this is of electron or that of the hole. By writing mu e or mu h with subscripts for the electrons or holes mobility, we can avoid any confusion between mu as the chemical potential and as the mobility. Okay, the electrical conductivity is the sum of the electrons and holes contributions. So we have the electrical conductivity given by the conductivity of the electrons in conduction band and the conductivity of holes in the valence band, and if small n is the concentration of electrons and small p is the concentration of holes. So this is the total mobility of the semiconductor given by equation 49. Okay, now you can go the rest of the paragraph here and also look at table 3, which gives us the various parameters, that is the concentration of electrons, concentration of holes for various crystals, diamond, silicon, germanium, etc. So this table must be carefully watched because this gives us the data for various solids, for various semiconductors. And you must also go to this paragraph to get some more information about semiconductors. Okay, now my next topic is the impurity conductivity, and I will come back to this topic in the second part of my lecture. Okay, thank you very much.